In our previous lecture, we made a brief introduction to state equation, which we claim is a very powerful tool to formulate circuits in particular and dynamical systems in general. Today we will obtain state equation for some example LTI circuits, and we'll get familiar with the object. Okay, our first example is the following circuit, okay, for which we will obtain the state equation. And remember that obtaining the state equation require some steps, and we will remember what those steps were while we go with this example. So it's a third order circuit because we have three dynamic components, two capacitors and one inductor, whose initial conditions we can pick freely. We have a single input in our system. Remember that by input or inputs we mean the voltages supplied by the independent voltage sources and currents supplied by the independent current sources throughout the circuit. So in this circuit we have just a single independent source, and it's this voltage source. Therefore it's our only input. R1, L, C1, C2. Here we have independent current source, R2. The inductor current is labeled as such. This is the voltage of the first capacitor. This is the voltage of the second capacitor. Okay. And for this example, we're asked to obtain the state equation describing this circuit. Okay. So what we said last time is graph theory is quite a useful tool in obtaining the state equation in a systematic fashion. Okay. So let's apply or let's get some help from graph theory. And if you choose to do that, our first step is obtain the graph of this circuit, and then using that graph pick a proper tree. And then what a proper tree is, we will remember, we'll review very soon. So let this be our graph describing the circuit. So we have 1, 2, 3, and 4 nodes. Okay, not that these are all the same nodes here, and this and that, they're the same. And then here we have the fourth node. Okay. So so this edge represents voltage source. This edge represents resistor 1, R1. This edge represents C1, and so on. So this is our second capacitor, and we have two other branches between these two nodes. So let's also show them in our graph. Okay. So this is our 4 node and 1, 2, 3, 4, 5, 6, 7 edge or 7 branch graph. So let's do labeling because we will need them when writing Cutset and loop equations. Let's call this 1 corresponding to the first capacitor. Let's call this branch number 2 corresponding to the second capacitor. Let's call this branch 3 corresponding to inductor, and so on. So the remaining branches are labeled as follows: 4, 5, 6, and 7. Okay, so this is a graph with proper labeling representing this circuit. Okay, so once we have this graph, what we do is we pick a tree. Okay, for this graph. And when we do that, because we eventually want to obtain the state equation, we have to be careful at certain points. Okay, so what we have to do is we have to pick a so-called proper tree, and the proper tree satisfies certain conditions. Let's remember those conditions. The proper tree should contain all the independent voltage sources in the circuit, and it should not contain any independent current sources. Okay, so that's one condition. If there is an idle transformer in the circuit, then the tree should contain one and only one of its branches. What else? Our proper tree should contain as many capacitors as possible, and also there is a dual condition: it should contain as few inductors as possible. Okay, so that's our definition of proper tree. Now, for a given circuit, there may be more than one candidates that would make a proper tree, but in this example, it turns out that there is just a single tree that satisfies all those constraints. Okay, so it should contain all the independent voltage sources. Therefore, this definitely belongs to our tree. Okay. About the idle transformers, since we don't have any transformers in the circuit, we don't have to worry about that condition. And then what else? The tree cannot contain any independent current sources. Therefore, we don't have any current sources, independent current sources in the tree. Therefore, that's also irrelevant for this example. And also, it should contain as many capacitors as possible. So let's include that for this capacitor 1, and also include this one because we can. Capacitor 2, and then we're done. Okay, this is a tree, and adding any further branch to the tree will make it a non-tree. Okay, there will unavoidably be a loop, therefore it won't be a tree. Therefore, this is our tree, and it satisfies all the conditions for us to obtain the state equation. Therefore, it's a proper tree. Okay. Now, this proper tree will help us in 2 points. One of those points where it will help us choose the state variables or the state vector. That's one thing. The other thing is, by writing the fundamental Cutset and fundamental loop equations using the proper tree, it will help us obtain the state equation. Okay. So let's remember what are the fundamental Cutset and fundamental loop equations corresponding to the capacitor branches and inductor branch. Okay, because later on we will use that. So this capacitor branch number 1, it defines a Cutset, and it defines many Cutsets, but it defines a single unique fundamental Cutset, and it's this. Okay, so it contains only a single branch from the tree, and all the other branches, 4 and 3, they're coming from the core tree. So this is our Cutset 1, Cutset generated by branch 1. How about the Cutset generated by the second capacitor branch? It's this. Okay, this is our Cutset 2. Okay. And also, we have a fundamental loop defined by any cotree branch, and we're not interested in any cotree branch, but we're interested in the branches that correspond to inductors, and we have in this case a single inductor. Therefore, let's also figure out the fundamental loop defined by this cotree branch number 3, and it's clearly this here. Okay. 3, 2, and 1. That's our fundamental loop defined by the code tree branch number 3. Now, cut sets will allow us, or will help us write KCL equations, and eventually those equations we will use in order to obtain the state equation. So let's write them down. Anyway, cut set 1. Okay. So there are 3 branches associated with cut set 1, 1, 4, and 3, and therefore, if you write KCL in that cut set, what you have is I1, okay, plus I3 plus this current, which is minus I4. Okay, so we're treating all the currents as if they are leaving the cut set. In this case, what we're doing is no other than writing the node equation at this node. And by KCL, this sum must equal 0. Let's do the same thing for the other cut set. Okay, so we have, let's start with I2, and I2 is, if you consider this as a cut set, is, we can consider it as if it's leaving the cut set. So let's treat all the currents as if they're leaving. So I2 is leaving, this current is leaving, and this current is minus I3. And we have I6 and I7. I6 plus I7. And by KCL, that should equal 0. Let's do the loop equation. Okay. We have just a single loop, fundamental loop associated to an inductor branch, and it's this. So let's write KVL V3. Okay, suppose that direction is determined by this inductor branch, which is in that direction. Therefore, we're talking about a clockwise rotation. So we have this voltage, V3, plus this voltage, V2, plus this voltage, which is minus V0. And by KVL, that sum must equal to 0. Okay, so that was our step 1. Step 2 is, okay, so this is our proper tree. Then we have step 2. Which says choose the state variable or the state vector, and state vector is such that it should contain all the capacitor voltages that belong to proper tree and all the inductor currents that belong to code tree. In this case, we have V1 and V2 as capacitor voltages that belongs to the tree. Okay. So X is usually what we use to denote our state vector. So we have capacitor voltage 1, capacitor voltage 2, because both capacitors belong to the proper tree, and we also have the inductor current that belongs to code tree, okay, which is I0. Therefore, we're talking about a state vector of size 3, dimension 3. Okay. Now, what we want is, having chosen the state variable, now we want to obtain the state equation. Find matrices A and B such that we have the state equation which has the following form: x dot equals ax plus b times input vector, which we usually denote by w, but in this case we just have a single input, which is vs, so we can just write it as vs. Okay. Vs. So x is in R3, it's a size 3 vector. Therefore its derivative is also size 3, and here we have a matrix. This is size 3, this is size 3, therefore the matrix A must be 3 by 3 size. Okay, so we're talking about a square matrix, and in state equation, this is always a state square matrix. And here we have B, it must be of size n, and being the order of the system, times n is the number of individual inputs that you have in your system. In this case, we have a single input, 1, and the dimension of the system or the size of the state vector is 3. Therefore, B has to be a 3 by 1 matrix, or in other words, it should be a column vector. Okay. Now, to obtain those matrices or the entries of those matrices, what we need to obtain is x dot. Remember, we have to obtain v1 dot, v2 dot, il dot, and we want to express those time derivatives in terms of our state variables v1, v2, il, plus perhaps the input, which is vs in this case. Okay, and in order to obtain those expressions for v1 dot, v2 dot, il dot, we will make use of the KCL and KVL equations we have just written down. So let's go ahead and obtain the state equation. Okay. Okay. So what we have is, so we had step 1 where we obtained a graph and then the proper tree. Step 2, using proper tree, we have chosen the state equation. Now comes step 3, or sometimes they consider steps 3 and 4. Okay. In step 3, you obtain the capacitor voltages or the time derivatives of capacitor voltages. In step 4, you obtain the time derivatives of inductor currents. But those 2 steps can be considered a single step. Okay, so let's call them steps 3 and 4. So let's obtain therefore x dot, or in other words, let's obtain v1 dot, v2 dot, and il dot. Okay. For that, you will use the Cutset and loop equation. So let's give them numbers. Okay, let's call this equation 1, equation 2, and let this be our equation 3. Now, using equation 1, okay, we have the following I1. Okay, so this was our first branch. So I1 is the capacitor current. Okay, and capacitor current is C1 dV1. Okay, so that's I1. Then we have minus I4. This was I4. Okay. Therefore, this is what we're talking about. So it's minus I1. Let's say direction of the 4th branch was like that, and finally we have plus IL, which is I3, okay. And that equals 0 by KCL. Now, from this equation, which we obtained using the Cutset equation, equation number 1, what we want is v1 dot. And we want to express it in terms of state variables v1, v2, il, and the input vs. Now, this il therefore is a nice term because it's one of our state variables, but we have a variable here, ir1, which is not one of our state variables. So we have to express it in terms of our formulation variables. And that's easy to do, at least in this case. So let's rewrite this example by re-expressing ir1 in a more useful way. So what we have is C1 dV1, okay, minus IR1. So this is IR1. Okay. What's IR1? IR1 is this voltage minus this voltage divided by the resistance in between. So we have Vs minus V1 divided by R1. Okay. Plus IL equals 0. Okay. Now in this new expression, everything is fine because we have dV1, V1 dot, and also all the remaining variables are state variables or the input, Vs, V1, and IR. Okay. So let's call this equation 4. And then we have equation 2, that's our other Cutset equation. I2 minus I3 plus I6 plus I7 equals 0. So I2 was this current, which is C2 dV2. Okay. And then we have minus I3. This was I3, therefore this is minus I3. So we have minus IL. And we have I6 Gn V1. And finally we have IR2, that current. But IR2 we can easily express in terms of our state variables, which is V2 over R2 plus V2 over R2 equals 0. This equation is also in a nice form because everything is in terms of our state variables and input. So let's give it a number 5. And finally, write down the KVL, define on the fundamental loop. Okay, equation 3 implies V3. This is plus minus V3, which is no other than inductor voltage. Okay, and that's therefore L VIL. That's our V3 plus V2 minus V1 equals 0. Okay, by KVL. This is our equation number 6. Okay. Now we have all the state all the individual scalar state equations. To obtain the actual state equation, or the state equation matrix form, therefore all we have to do is reorganize the terms. So let's do that. Okay. So let's rewrite 4 by putting dV1 on the left hand side and removing everything to the right hand side. So dV1 equals, okay, we're using this equation now. dV1 equals minus 1 over R1 C1 V1 minus 1 over C1 IL plus 1 over R1 C1 Vs. And then let's do the same thing to the remaining equations, 5 and 6. 5 will give us dV2 in terms of state variables. dV2 is minus Gn over C2 V1 minus 1 over R2 C2 V2 plus 1 over C2 IL. Okay, and finally, for DIL, we use equation number 6, which you obtain using the KVL on fundamental loop. DIL equals 1 over L V1 minus 1 over L V2. Okay, now that's just a rewriting of this last equation. And now we're ready to obtain the state equation, or in other words, obtain A and B matrices for this state choice. So that's our final step, putting all those individual scalar first order equations into a single matrix equation, a single vector equation. So what we have here is x dot equals 3 by 3 matrix A times x plus the 3 by 1 matrix B times A. Yes. So this is our A matrix and this is our B matrix. And our state choices V1, V2, I1. Okay. So here we already have x dot, okay, V1 dot, V2 dot, I1 dot. So for the first row, we look at the first equation, V1 dot equation. So what we have is V1 dot equals minus 1 over R1 C1 times V1. Then plus 0 times V2, because V2 doesn't appear in that equation, minus 1 over C1 times IL And finally, plus 1 over R1 C1 times Vs. Okay, so the first equation gave us the entries in the first row. Then we look at the second equation, or the equation number one, right? Second equation for the second row. Second state variable was V2, so we're talking about V2 dot. V2 dot equals minus Gm over C2 times 1, and minus 1 over R2 C2 times V2, plus 1 over C2 times IL, and plus 0 times Vs, because Vs doesn't appear in the equation, so that means we have to put a 0, okay, for that entry. And finally, for the last equation, we have 1 over L minus 1 over L for V2. We have no IL term, so that's 0, and we have no Vs term, so that's also 0. Okay, so that's our state equation for the state choice V1, V2, right now. Now let's move on to another example. This time we have an ideal transformer in our circuit. With turns ratio 2 to 1. Okay, so we have 1/2 farads, 1/2 farads, the same here for this capacitor. It's 130 henries for the inductor. This is 3 ohm, this is Yes, okay, plus minus V1 plus minus V2 is the second capacitor and also second coil, second right coil voltage, and that's also labeled the transformer currents as I1 and I2, and as for inductor current, it's given in this direction and it's labeled IL. Okay. Now let's, for this example, obtain the state equation. Okay. So let's therefore pick a tree. For that we have to quickly obtain the graph and pick a proper tree. So let's do that. Here we have a node, here we have another node, here we have another node, here we have another node. Again, we're talking about a 4-node circuit. Okay, so let those nodes be like this. Okay, and here. So this is the 3 ohm resistor. This is the independent voltage source. Let this be the first capacitor. Let this be the first coil. Let this be the second coil. Let this be the second capacitor. And finally, let this edge be the inductor. Okay, so let's give them directions. Okay, so that's our graph. Now, for this graph, let's choose a property, because property will help us to choose a state variables or the state vector. First of all the independent voltage sources must belong to our tree. Therefore, this branch that describes independent voltage source is part of our tree. If we have an ideal transformer, in this case we have one and only one of its branches must belong to tree. Okay, therefore you can choose this branch, and the other branch must necessarily be outside tree. Okay, and finally, okay, we should contain as many. Okay, we should contain as many capacitors as possible in our tree. We have two capacitors here, so what we want is, we want, for instance, both of them to be in our proper tree. Not that we, for instance, that capacitor is represented by this branch, so let's take this branch as part of our tree, and also we want to include this capacitor too. But if you include that capacitor in your proper tree, then what happens is, here you obtain a loop. But in that case, that tree is no longer a tree, therefore we cannot include this capacitor, okay, in our tree. And then perhaps you can say, what if we have chosen the other transformer branch? Can we increase the number of capacitors in our proper tree? Then it turns out that for this example, at least if you choose this branch instead of this branch, again you can only choose one of the capacitors in your proper tree. So there's not really any difference. Okay? So therefore this is our proper tree, and using that proper tree now we're ready to figure out our state, and then the state equation. So this is our proper tree, and from the proper tree we're going to take the state. Let's begin our solution. State or state vector is, okay, all the inductive currents in the core tree must belong to our state. So we have a single inductor. So that's one of our state variables. And all the capacitor voltages in the proper tree must belong to our state. In this case, even though we have two separate capacitor voltages, only one of them is in the proper tree, which is V2. Therefore, we cannot include V1 in our state. V2 should be our other state variable. Okay, therefore we're talking about two state variables, meaning that we're talking about a system of order 2, a second order system. And once we have the state vector, the next step is obtaining IL dot in terms of IL, V2, and input Vs. Likewise, do the same thing for V2. That is, obtain V2 dot in terms of IL, V2, and Vs. Once we have those individual scalar equations, we can easily put them in the matrix form, okay, which we call the state equation. Okay, so let's do that. Cutset equation. Okay. For the fundamental Cutset, described by the capacitor that belongs to our tree. So we're talking about basically this Cutset here, and we're talking about a known equation. Okay, write a known equation here. So we have this current plus that current plus this current must equal 0. Okay, so we have the capacitor current, which is 1/2 dV2 by the terminal equation of the capacitor. Okay, plus this current. For now, let's call it I2. Okay. That's current of the second coil of the transformer. And finally, we have this current, which is minus IL. Okay, so let's call this equation 1. And for the KVL part, let's look at the loop equation defined by the branch representing the inductor. The fundamental loop is this voltage, it contains this branch, and that branch. Okay, remember that fundamental loop is such that it contains only a single branch from the code tree and all the other branches coming from the tree. Okay, so therefore we're talking about this branch, and that branch. Okay, if you write the loop equation, you have this voltage, which is 1/3 DIL, that's the inductor voltage, plus this voltage, which is V2. Okay. And plus this voltage, which is minus V1. Equals 0. So that's our second equation. Okay. And from those equations, we will obtain A and D matrices. But immediately, you will recognize that in these equations, we cannot directly go to, from these equations, we cannot directly move on to x that equals AX plus BVS form, because there are certain variables that are not our state variables. For instance, I2 is not one of our state variables. Likewise, V1 is not one of our state variables. So therefore, before going to x that equals AX plus BVS form, we have to somehow express I2 and V1 in terms of our formulation variables. Okay. So we ask the following question: what's I2 and V1 in terms of formulation variables? That is, the state variables IL, V2, and input Vs. Okay. Let's do that. Note that so far we haven't used the terminal equations for the ideal transformer, so we have to at some point use them. So let's do it. So the terminal equation that links the voltages for the ideal transformer is V1 over the first turns ratio equals V2 over the second turn ratio. We're talking about V1 over 2 must equal V2 over 1. Okay, so that's our equation. And from this terminal equation, we immediately obtain V1 in terms of our formulation variables. Okay, V1 equals 2V2. Let's call this equation 3. Okay. Therefore, by replacing this V1 with 2V2, this equation becomes, or gets into a nice form. But still we have to take care of I2. So let's do that also. For that, let's use this time the other term equation for the ideal transformer, which is 2I1, okay, plus I2 equals 0. So that means we can write I2 as minus 2I1, okay? But still, this is not helping us either, because I1 is not one of our state variables, so we have to go further. And that equals 2 times, so this is I1, this is minus I1, 2 times minus I1. And what's this current? This current is this current, that current plus IL. Okay. So we're talking about 1/2 dV1, it's the current of the capacitor, plus that current, which is V1 minus Vs divided by the resistance in between, and finally plus IL. Okay, so that's I2. And that equals Okay, so V1 is not one of our formulation variables. What we have to do is we have to replace V1 with 2V2. Why? Because V2 belongs to our set of formulation variables. So let's do that. And if you do that, we have I2 equals 2dV2 plus 4 over 3 V2 minus 2/3 Vs plus 2IL. Okay, so that's what I2 is. Let's call this equation 4. Okay. Now we have I2 in terms of the formulation variables. Now we're getting closer to the result. Let's combine equation 1 and equation 4 to obtain dV2. Equation 1 and 4 implies 1/2 dV2 plus I2, and now we have this expression instead of I2, so let's write that down. Plus 2 dV2 plus 4 over 3 V2 minus 2/3 Vs plus 2IL. Okay, this whole thing is I2. And finally, in equation 1, we also had IL. So minus IL equals, so we rewrote equation 1 by replacing I2 with this expression. Okay, and that will give us nicely dV2 or V2 dot. dV2 equals minus 2 over 5 IL minus 8 over 15 V2 plus 4 over 15 Vs. This is our equation. Finally, this equation is clean in the sense that it contains no formulation variable, no variable other than our formulation variables. Let's do the same thing for equations 2 and 3. So what we had was 1/3 DIL plus V2 minus V1 equals 0. And now we know that V1 is 2V2, hence we have 2V2 for V1, and that equals 0. Okay. Let's reorganize that, and we can write DIL equals 3V2 equal to 6. Okay. Now we're almost done. All we have to do is put equation 6 and 5 into x that equals ax plus bvs form. Okay. 5 and 6 yields x that equals ax plus bvs. Okay. And x, our state choice was IL and V2. So, for the first row, we look at the IL equation, which is here, equation number 6. So, the IL equals 3V2, meaning it is 0 times IL plus 3 times V2 plus 0 times Vs. Okay. For the second row, we look at the V2 dot equation, and it's here dV2 equals minus 2 over 5 IL minus 8 over 15 V2 plus 4 over 15 Vs. Okay. Therefore, this is our x that equals ax plus dvs state equation. So note that even though we had 1, 2, 3 dynamic components in this circuit is of order 2 2. Because by a state of size 2, state vector of size 2, we were able to formulate the circuit. So let's put that remark down. And move on. Given a circuit with state equation x equals ax plus b w with x being a vector in Rn, a vector of size n, the number okay, this integer is the order of the circuit, is called the order of the system or order of the circuit. Okay. So that means you have to know the n individual initial conditions in order to be able to, plus the knowledge of the input, in order to be able to figure out the future of the circuit, the future evolution of the circuit. Now, somehow related to this remark, let's consider, associated to the previous numerical example with ideal transformer, let's discuss the following point very briefly. So what's wrong with the following? Okay. Suppose that I ignore the procedure of choosing the proper tree, and I just in a blunt fashion, I just chose my state vector so that it contains all the inductor currents and all the capacitor voltages. So in this case, we're talking about a state of size 3, IL. We will have IL, and then we have V1 and V2. Okay, so let's do that. What happens? Let's see what happens. Ignore the proper tree. Suppose that we did that. And choose the state, okay, in quotation, because it's not really a state, but suppose that we think that we're choosing the state Z, let's call it Z, so that it doesn't get mixed up by that X. Z is IL, V2, and also the first capacitor voltage, V1. Okay. Then we can proceed as follows. We know that due to the transformer, V1 and V2 are fixed or related to one another through a fixed algebraic equation. Okay, V1 equals 2V2. So this immediately gives us V1 dot equals 2 V2 dot. Okay. And that therefore equals, so we have V2 dot, it's here. Okay, V2 dot is here. So multiply this by 2 and you obtain V1 dot. So let's do that. Minus 4 over excuse me. Right. Okay. So this should be fine. Sorry. So minus 4 over 5 IL. Okay. Minus 16 over 15 V2 and plus 8 over 15, yes, okay. So all we did is we multiplied both sides with 2, and then 2dv2 is no other than v1 dot, because v1 equals 2v2 by the terminal equation of the transformer. Okay, and then call this equation number 7 and combine equations 5, 6, and 7 and write z dot equals something times z plus something else times vs. Okay, so 5 and 6 and 7 implies z dot equals Vs. Now we obtain a state equation which is larger than the earlier obtained state equation. Z dot equals 0, 3, 0, 0, minus 2 over 5, minus 8 over 15, 0, 4 over 15. And now that this part here, this 2 by 2 block, directly comes from our earlier state equation. And these are 0 because in our earlier state equation, V1 didn't show up. Then we have the last row, minus 16 over 15, 0, 8 over 15. And the last row is simply this guy here multiplied by 2. Okay. Now, the question is this equation incorrect? The answer is no, it's correct. We didn't make any assumptions, okay? We just use the terminal equations, okay? The information coming from the circuit. So this is true, okay? But still, we don't call it, or we cannot call it the state equation, okay? And the reason is, it's not a minimal representation of the circuit, okay? In the sense that, if you consider this as the minimum representation of the circuit, then by definition, it should be that your circuit is of order 3, because the state vector is of size 3. And that means, again, by definition, that you have to know all the initial conditions, all 3 individual things. Or you can choose all those 3 initial conditions arbitrarily, but that's not the case. Okay? Because V1 0 must equal 2 times V2 0. So you don't have the freedom of degree 3, the only freedom you have is of degree 2, and that's why this circuit is second order. Okay. So let's write that down, and then we can end this lecture. Okay. Here is, so this was our question, what's wrong with the following, and this is our answer. Although equation star, okay, is correct, it is not, nevertheless, a state equation describing the circuit, because Z, our fake state, okay, is not a valid state. Okay, and that's because it is not minimal. Okay, in the sense that, in fact, we cannot choose the initial condition Z0 in R3 arbitrarily, okay, due to constraint V1 equals 2V2. Because V1 0 must equal 2V2 0. And the message to take home is that proper tree helps us see how to choose the state, the proper state. Proper tree helps us choose a state that is minimal. So by definition, the state must be minimal.